Okay. So now for the business that's hopefully sort of the freshest in everybody's minds. The last two things, well, not that one. Last two things that we covered, organometallics, and then who knows why they wait to the very end, but amines. Where are you? Okay. All right. First thing that I feel like I just want everybody to make sure that they remember is what's going to be the reaction between an amine and a carboxylic acid?
In amine?
No. So this is like the grand mistake that everybody wants to make, is because you're automatically thinking carboxylic acid derivative to carboxylic acid derivative. The first thing that we need to remember about amines before we start thinking about them as nucleophiles is that they play the role of bases as well. Right? So in this particular, it's even easier than what you were thinking, right? The very first sort of thing about amines is they can play the role of a base and accept a proton. So instead of being like our normal carboxylic acid derivative swapping functional groups, it's just going to play the role of a base. Okay, so again, it's kind of whatever that we waited to talk about amines until the very last chapter, because we had already seen a ton of reactions where they're playing roles of a nucleophile. But we just got to remember that, you know, first and foremost, they'll accept any hydrogen that is willing to be given up. Okay, where do I have this lecture? I mean, yeah, you're absolutely right. Like, one of the most prominent places we saw amines is when we were talking about carboxylic acid derivatives, where this group got swapped for our amino group and for our amine group, and so we created an amide. Okay. Another, again, sort of easy to overlook. What reaction would you get if it wasn't a carboxylic acid derivative, but just a ketone? See if you can't give me the product of these reactions here. This actually might fall more under the category of the ketone aldehyde chapter, but nonetheless, something we want to keep in mind. This was under slightly acidic conditions, not crazy acidic, but actually, let's do this. Okay, so if you have a primary amine or ammonia, you're going to get, and I think I said the wrong name when we were doing the last review video, something that looks like this, which is an imine. Okay, so something kind of bizarre looking. Notice that I've swapped out my one nucleophile, the oxygen, for the other one, a nitrogen, when I've created my imine from a ketone. What about when I have a secondary amine? I can't have that double bonded nitrogen anymore because it's already got two substituents. And so the other bond goes there, and this is an amine. Okay, so when you have nitrogen or some amine reacting with a carboxylic acid derivative, As long as it's not carboxylic acid, you'll just have a swapping of those functional groups. But if it's a ketone or aldehyde, you form one of these, I think, very bizarre looking compounds here, an imine or an enamine. Okay. So now let's do, so we had, in terms of like preparation of amines, we had two very similar ways. Gabriel and azide. See if you can't remember what those reagents actually looked like for creating primary amines.
The Gabriel was that big funky looking
The big funky looking thing, yeah.
Yeah.
Do we actually need to memorize that structure, or could we just call it Gabriel's?
You don't have to memorize it, but what I want you to do is see if you can't remember it, because what is going to happen is they're not going to call it Gabriel. They're just going to put a picture of it down.
Yeah, I can remember it by look, but I can't draw it.
So I really want you to recognize. Yeah, so just, I mean, do the best you can, but our whole point here is I want you to be able to sight recognize these things. Okay, so Gabriel, again, whole goal just being able to sight recognize it. That's this ugly looking thing here. I have the benzene ring attached to whatever that guy's called. I feel like I should know, but whatever. And sodium and azide is, you know, sodium azide N3. So this is where we have, in terms of what the actual like ion looks like, right? N3, nitrogen, nitrogen, nitrogen. So then you have sort of each of your nitrogens have a formal charge, but the net formal charge on that would be -1. So it's in salt with sodium. Okay, but those are our two methods that we learned of forming primary amines. They're super duper limited, so I don't, you know, I honestly don't know how commonly they are used in the lab, but because they do seem very limited, but yeah, we learned about them, so. Okay, and then.
Question about the Gabriel's. For that second part, is it two hexane rings? Well, one's a benzene and one's a hexene with a nitrogen on one of the parts?
One's a benzene and one's a pentane.
Pentane. Okay.
Okay. And then the way more flexible method that we learned about was, let's take a ketone. And again, first we're going to add and again, what is going to be the product of these two reactions? Take a second and tell me. I'll be right back. What's the product of this first reaction? What is that guy called?
Amine.
So that is going to be our imine. And what about the bottom one?
Amine or whatever it was.
Yeah, so that'd be the enamine. But these were all intermediates in making an amine because we would hit it with a reducing agent. Wow, that's not how you spell agent. That would create, oh, this was an R group, sorry. In this case, a secondary amine. In this case, a tertiary amine, right? So these were these more flexible methods of making an amine because the top two, we could only ever make terminal primary amines. Using Gabriel synthesis or sodium azide synthesis, you can, not only can you only make a primary amine, but because it relies on an SN2 type reaction, it can only ever be in a terminal carbon as well. So this method is way more flexible. Not only can we make primary amines that aren't terminal, but we can also make secondary amines and tertiary amines. There was a specific reducing agent that we learned about using. So if you did this in 2 steps, you could use sodium borohydride, lithium aluminum hydride, whatever. But the one that we learned about specific to this chapter is similar to sodium borohydride, but instead of having 4 hydrogens, you have 3 hydrogens in a cyano group.
Yeah, that's the last
Right.
one I remember.
Now, why? Why did we learn about this whole new reducing agent? Okay, so the reason is that if we used sodium borohydride, for example, or worse, a lithium aluminum hydride, that reacts with ketones and aldehydes to form alcohols. Sodium cyanoborohydride, our new one that we learned about, it doesn't react with ketones or aldehydes. It specifically reacts with imines and enamines. And the whole shtick is that then you can put everything in one pot and you don't have to worry about any side reactions. Okay, so it's nothing too fancy. It's just another reducing agent. But the whole idea is like thinking practically, not pencil and paper organic chemistry. We want to be able to just dump everything in and let it go. We don't want to have to do these steps where then we isolate and all that good stuff. Okay, so that's why we learned about this new reducing agent. So instead of seeing it in these 2 steps, what you would just see is something like ketone or aldehyde, you know, H2NR, under slightly acidic conditions. I should have put that here. And then sodium cyanoborohydride along with it. And that would generate, oh my gosh, getting sloppy. Your, in this case, secondary amine. Okay, so out of the methods that we learned in this chapter, this is by far the most flexible in that you can create any such amine out of it. Okay. Another reaction that we learned about was take an amine and add in some alkyl halide, usually an alkyl iodide is what would be used in this case. And what ends up happening? Everybody take a second and draw me my product.
All right, is this just with one equivalent?
Can't be, it's never like, you don't have any control over how many get added. That's part of the complication of this here. Remember, like one equivalent, I'd still have billions of molecules when I'm mixing them together. So then you would just get a distribution of somewhere 1's added, somewhere's 2's added, et cetera, et cetera. So yeah, sort of where Dylan's going here is the fact that you are going to have all of those methyl groups are going to be stuck onto that nitrogen.
Because it
right?
becomes a better.
What's up?
No, go ahead.
and the kicker here is like, and the reason why I'm saying, you know, the one equivalent, whatever, once you've stuck one on there, it's like that much more likely that the next one's going to get stuck on there and that the next one's going to get stuck on there. So even if you had a one-to-one equivalent, you would have a huge amount of your quaternary ammonium salt that's formed. Okay. Now, what we really start, I mean, this is, I don't know any situation where your whole goal in life is to make one of these quaternary ammonium salts. So the other sort of thing that we saw it paired with is this set of new reagents here.
And
what does that do for us?
cleaves the amine and forms a double bond.
So basically now we have this really good leaving group here. So this is just an elimination reaction. You could probably do it with any old base, but specifically in this chapter, we now saw this new set of reagents using silver. So again, just in terms of site recognizing reagents, this should be kind of a clue to you about what's happening. And not only is it do we have an elimination reaction, but it's an elimination reaction that goes in the other direction than what we would think, right? Normally when we have elimination reactions, we have the formation of the more stable, highly substituted alkene. In the case of the ammonium salt, we specifically get what's called the Hoffman product, or where it's not. And I'm not going to go too far into it, but you can go back in the lecture and look. Basically, it has to do with sterics. Okay, but just have in your mind it's going to be the you're going to get elimination to the less highly substituted carbon. Okay, and again, this sort of set of reagents here was one that we learned about new in that chapter. Okay. All right, there were these, just to sort of refresh, we had these various reactions with nitrous acid. In the case of a secondary amine, you formed this very weird looking thing called an N-nitrosamine. All we really know about that is that it's terrible for you. If instead of being a secondary amine, it was a primary amine, and this is the one that I think is probably the way more important of the two reactions, we get what?
I forget what it's called, but just the nitrogen triple bonded to another nitrogen.
Yeah, so you get this guy here.
The diazonium salt?
Yeah, the diazoniums.
Yeah.
Okay. And this is particularly important when not just any old R group, but I mean, again, if I had to bet where you were going to see this on the ACS exam, it would be with regard to aniline and the creation of a diazonium salt, right? And so where I really see this happening is in some sort of a multi-step synthesis sort of thing. And why would I think that this would be a part of a multi-step synthesis problem? What is this group doing for us, this diazonium group?
It's a good leaving group, right?
It's a good leaving group. That's the thing that I want to have drilled into your head. When you see this kind of functional group right here, you're thinking to yourself, good leaving group. Okay, so really what I foresee kind of happening on an ACS exam is, right, because there's that section, that multi-step synthesis section, right? So I foresee something like this. Okay, so everybody give me the product that you would get in this multi-step synthesis problem here. we can even, because this is what Bryce brought up earlier, make it a cyano group. Okay, so what's going to be the product of this first step here? Especially those of you that were in my last review section. What's it going to be?
The nitrate.
So after our
It's going to
first,
be aniline.
yeah, we'll have the NO2, right? So that nitro group. Okay, so that's step one. What's our, and these two are actually together, they're grouped together. What's that next step going to do?
Changes it to aniline.
And change it to aniline. And again, it could be zinc, could be iron, could be tin. Just think any metal plus HCl, and then the next step being base. We're going to convert our nitro group to an aniline. Okay, so that would be our next step here. Let's finish this off. And then step 4, what's that doing for us?
The diazonium.
The diazonium. And then our last step, again, when you're thinking that diazonium, you're thinking
Leaving group.
leaving group. And so that's just going to replace that with this cyano group. So these multi-step synthesis problems kind of suck. They're kind of hard, right? But if you can sort of recognize, like, let's say I forgot what steps 2 and 3 are going to do, but then all of a sudden I recognize that Na, NO2, and HCl, that's our diazonium thing. That kind of gives you a clue that before that, you probably had to have an amine group there. We don't know what else to do with that, right? So sometimes, you know, obviously if you could take a multi-step, step-by-step, that's great. But sometimes looking down the line and thinking, okay, well, what do I know how to do with that reagent can help give you a clue as to what the step before it's going to be. Okay. I haven't seen the exam yet. I don't know that this is like exactly how it's going to show up. But again, that is the #1 use for this nitrous acid, is creating a diazonium group on an aniline for the sole purpose of making it a good leaving group. Okay. We saw a bunch of examples where copper and some other nucleophile is what's doing the substitution reaction. There were 2 other ones that I want to point out just because I think that they're a little bit less obvious. And that is H2, H3, PO4. So give me the product of these reactions here. Take a minute. PO4 do? Anybody?
What? You could have.
Just,
Oh, sorry, the H3PO4, what does that do for us?
it just,
takes it off, right?
yeah, it takes it off.
That just replaces it with a hydrogen. So what a hilarious pain in the butt multi-step synthesis problem this could have been if at the very last step I had put H3PO4, and then we would have had this very roundabout way of going from benzene back to benzene. But I honestly do not put it past the ACS exam at all to do something like that.
If is there any specific groups that H3PO4 won't take off?
It's only this guy here. It's only
Okay.
your night. Like that is just right. So this is actually just an electrophilic aromatic substitution reaction, or a nucleophilic aromatic substitution reaction. But remember the last time we learned about that, you needed to have like these either crazy conditions or an electron withdrawing group. The diazonium group is just the most primo of leaving groups, right? So it's very easy to swap it out for any other nucleophile. But yeah, this is the only way that we know to chop that off, is with phosphoric acid, is starting out with that diazonium group. And then if we use instead water and heat, what does that do?
Alcohol.
The alcohol, yep. So that will create a phenol. And actually one more is if I take that diazonium group and I add phenol.
With the azo
Yeah,
coupling?
the azo coupling. And again, this kind of seems like a bizarre reaction, but it's just one of the ones that the ACS loves, so it's a good idea to know it. And that OH group could be any good electron donating group. So another common one would be like an aniline, or even if there was an ether group like an anisole. Okay. There's something. Why do I feel like there was something else that I wanted to do? Oh, and I guess just to hopefully have this hammered in your head as well. Speaking of electrophilic aromatic substitution reactions, everybody give me the product of these two reactions using these nitrogen heterocyclics.
The 0 is going to be at the C2 carbon, and the high is going to be at the C3 carbon.
Yeah, I mean, that's the real important thing to know about these reactions, is that they are stereospecific. You're only going to get one stereoisomer out. In the case of pyrrole, it is at the C2 position. And in the case of pyridine, it is at the C3 position. And I feel like it's going to suck up too much time, so I don't want to go into it. But remember, we used resonance to justify this, right? So you could do the resonance structures of these intermediates to show why each one of these positions are preferable. You can look at the discussion answer key for this particular, the nitrogen heterocyclic problem set, and it goes through those resonance structures illustrating why, and I explain why, one position is preferred over the other one. Okay, so that's all done out in the answer keys for that particular discussion. All right, last one here, organometallics. Okay, so first of all, okay, give me the product of these three reactions. Okay, what's the functional group that I'm going to get in my reaction with my Gilman reagent, the organocuprate?
Ketone.
A ketone. So this sort of, again, how I think about Gilman versus Grignard, right, is Gilman is a weak organometallic compound, where Grignard is a strong organometallic compound, right? So your weak organometallic, it can react with an acyl chloride, but it can't go on to react with the ketone that's produced. Whereas our Grignard is a strong nucleophile. So what's my functional group going to be?
You'll get an alcohol, and then the R will be on there twice.
Yeah, exactly. It's going to be an alcohol, and I guess I gotta be messy. This acidic workup business after that. All right, and then again, like, I don't think in the lab you will ever see this, but let's say that the ACS throws you a compound that is organolithium. What are you immediately going to think?
Grignard.
It's exactly the same as a Grignard. All right, have those together in your. Truth be told, this is always used as a precursor to make a Gilman. But if they just give you an organolithium all by itself, you're going to just treat it exactly as a Grignard. So in this case, I'm going to have the same product as I had with my Grignard. Again, the reason is lithium's like literally 10 times more expensive than magnesium. So why would I use an organolithium if I could just use an organomagnesium? But again, pencil and paper organic chemistry, what the ACS might throw at you, you want to have these two in the same place in your mind. Okay. So your exam 4s should be done, hopefully realistically you'll get them on Friday. And I built those Suzuki and Heck problems into Canvas so that you guys can study them afterwards. So you have like an answer key that you can look at to get through those. So let's just do a few real quick, but again, those will be good study tools once that's opened up. Let's actually, I lied. Let's just talk about Still versus Suzuki and when you're going to use which one where, right? Because they're both very, very similar, right? You're going to have an organometallic reacting with an alkyl halide in both cases. First of all, what is the metallic? What is the metal for a still reaction?
SnBu3.
Yeah, so Sn is tin, right? So this is like this tin-based organometallic, but yeah, with 3 butyl groups. And what is it for a Suzuki?
YB2.
So the important one, so there's something on the boron. The
Oh,
important
where
ones
is
to
it?
remember is you have tin with some crap attached to it, or you have boron with some crap attached to it. Okay, that's our two different reagents, or 2 different organometallics. Okay, our alkyl halides have the same restrictions for both of these reactions. Does anybody remember what those are?
Aryl vinyl.
Yeah, so they're kind of our default that all categories fall into. They're just aryl or vinyl. Aryl or vinyl. And then actually our organometallics can also be aryl or vinyl. But they can also be a few different things. What are the other 2 groups that they share?
What is it?
I think one's benzylic.
One's benzylic,
Allele.
and then the allylic. Right, benzylic, remember, is this position here, 1 carbon removed from a benzene ring, so like it still can be in resonance with the benzene ring. And similarly, an allylic position is 1 carbon removed from an alkene, so it can still be in resonance with that alkene. Okay, so this would be, you have your so this would be a benzylic. This would be allylic. Right, versus you sort of this would be aryl, so now it's directly attached to a ring when it's aryl, or vinyl directly attached to that sp2 carbon. Right, and so this is the one that they all share. Benzylic. But then Suzuki is special. Why?
It can be an
Alkyl.
Alkyl, which is a very general group, right? That's just like an sp3 hybridized carbon with no double bonds around. So that's why Suzuki is kind of like, I don't know if I'd say the default one, but it's sort of the more common one because it's got that broader amount of substituents that you can use. They have the same restrictions on the alkyl halides. So when would I use a still reaction instead?
If there's a functional group.
Exactly. Suzuki reactions are not compatible with other functional groups. So with and that's kind of a blanket rule. It's really functional groups that have any sort of acidic hydrogen, including ketones or aldehydes, because of their alpha carbon. We don't really think of ketones or aldehydes as being acidic functional groups, but nonetheless, they sort of fall into that category. So blanket statement, let's just say it's not compatible with other functional groups, because pretty much every other functional group we know will either have an acidic proton or have an alpha carbon. Okay, so that's why we're sort of making that blanket statement. All right, so then just in terms of, we got 15 minutes. All right. So let's just do a few examples here. Oh, that's not what I wanted. Okay, wait. I'm gonna get rid of this. All right, so I want everybody to do these retrosynthesis problems where you're going to use either a still or a Suzuki. If you can use both, just pick, and you're going to make each one of these our part, and I'll keep it up there because you all have it on your paper probably, so it doesn't make sense to get rid of it, is to figure out which fragment's going to be which fragment's the organometallic half and which fragment is the alkyl halide half. Let's do this. Oh, crap. I'm in there. Sorry, I messed up on this one. The other one would have worked too, but it wasn't going to prove my point. Okay. So again, I got a jet like right at 2, so we're going to kind of have to breeze through this real quick. Again, if I'm going to tell you that they're going to be made from a Still or a Suzuki, which bond, 1, 2, 3, 4, 5, is my newly created bond here?
2.
So that means this bond right here is the one that's going to be new. Okay, so I'm going to just break these. I'm going to be lazy and use my computer, break these 2 fragments apart, and now I got to figure out which one is which. Which one's going to be the organometallic half, and which one is going to be the alkyl halide half.
It doesn't matter.
So my tiny little fragment here, what's that going to be?
I think it's the halide.
So the halide, first of all, is it Still or Suzuki? Let's start there, actually.
Still.
It's got to be Still because I have that functional group.
And I can't
So
remember.
Still reactions are compatible with other functional groups. The only caveat is that that functional group has to be on the halide half. The reason is because to prepare that organometallic, you have to use a Grignard, and I can't prepare a Grignard with this fragment right here, or it's going to react with itself. So although once I have my Still, I can react it with this and we're all good. Bottom line is functional group has to be on the alkyl halide fragment. Okay. I had originally messed up on this one, so sorry if you copied it down differently, but this is where I wanted to go. One of these bonds, I mean, it's symmetric, right? So this bond right here is going to be my newly created compound. Which half is going to be my alkyl halide half, and which one is going to be the organometallic half? Right. So the easiest thing to do would be to sort of class it. So, you know, if I'm going to shop at this bar, what would this fragment on the left be? Aryl, benzyl, vinyl, allylic.
Aryl.
So this would be aryl. And then what about the other side?
Benzoic.
Or benzoic.
This would be benzyl. And so what has to be what?
Aryl has to be the halide, and then the benzyl has to be the organometallic.
Yeah, so if we look at our little cheat sheet as to what's allowed, the only thing that our alkyl halide can be is either aryl or vinyl, right? It can't be benzyl. So that's how I know that this fragment is the alkyl halide half. And this fragment here is my organometallic half. It wouldn't matter whether I chose Still or Suzuki for this particular reaction. Either one of these would have worked because benzyl falls into the category for either. Okay, then down below, Still or Suzuki?
Suzuki.
Suzuki.
Yeah, so this one has to be Suzuki. And why is that?
That is the alkyl group.
Because we got the alkyl group. Now, the only other thing about this one to keep in mind that's important is stereochemistry. I mean, it's kind of nice that it works out the way it does. There's no funky business, but these reactions will preserve stereochemistry. So that means that, okay, I have my organometallic half as my alkyl chain. My halide has to have that same Z stereochemistry. I guess I can use a different halide since I can use that. Okay, so stereochemistry will be preserved in these reactions. So that if I'm going back and looking at my fragment, I just need to make sure that those double bonds have that same stereochemistry.
Could we have also split it at the other side of the double bond and made that just that propyl, the
Yeah.
organometallic?
Yeah. I mean, yeah, I mean, to be honest, typically we, the only reason that that looks weird is because we've always sort of seen every example that the book gave had the organometallic as a terminal functional group. I don't know any reason why it couldn't be on a secondary carbon, but just everything we saw, it was on a primary carbon. So just sort of drawing conclusions from what the book has given us, I might assume that, you know, although we couldn't pencil and paper break it up either way, in the lab, it probably works more efficiently if it's on a primary carbon.
Okay.
Okay. What we got? All right, real quick. Heck reactions, sort of similar consideration. Let's do this. All right, if I'm going to use a Heck reaction, what two fragments would I have to use in order to create this? Everybody take a second. Okay, so sorry, for the Heck reaction here, I have two different possibilities, right? Heck is between an alkyl halide and a just a regular old alkene in the presence of some palladium catalyst. I should have mentioned that about Still and Suzuki as well. These are all three reactions that were catalyzed by palladium. So if you see palladium on that ACS exam, you're thinking Still, Suzuki, or Heck. So for the Heck reaction, I have two options as to what could be what here. Who thinks it's A? Everybody raise your hand. Okay, and who says B? Okay, it's actually A. Okay, and I think if you said B, you might have been tempted because this back half is bigger than this half. And it's true that for the alkene, the smaller fragment is ideal. It will react faster. The important thing about a Heck reaction, though, is the alkene fragment will always have substituted the most accessible hydrogen. So if we used B down here, it would be this hydrogen that would be substituted, and my product would be however many friggin' carbons. The stereochemistry of both double bonds would be E. Basically, the alkene fragment, alkene, will always have the E stereochemistry. So if my product has any Z stereochemistry in there, that has to have been on the alkyl halide half. Okay? All right, and then last one here are these metathesis reactions. There are two possible catalysts that we could use. Does anybody remember them? They're two dudes' names.
Simmons Smiths.
Nope. So Simmons Smith is where you create the triangle. This is for a metathesis. We're going to close this ring here.
Rub.
Or
Shrubs is one of them.
Shrugs.
Yeah. Okay. Either one of those names you could see on the ACS exam. Both of those are going to do these metathesis reactions. Right. And the important part to note there is that the double bond is going to be chopped. Right. So I'm going to cut here and cut here, which means that the members of my ring are going to be those guys there. Basically, you're going to have to remove two carbons, one from either side of each of those double bonds. Okay, so you're losing carbons when your ring is closing. And on the opposite end, if we had a ring opening reaction, we would be gaining carbons. All right, I got to throw this down and dip out. 1, 2, 3, 4, 5, 6. 1, 2, 5, 6. Should have a double bond between 1 and 6. I have a methyl group coming off of carbon 2, and I don't have a carbon at position 3. I have an oxygen. All right, I got to dip, guys. If you guys have any questions, let me know via email. I will have office hours next week during finals week, so if you're doing any studying and you got any questions, let me know. I'll be available via email. I could probably meet on Zoom for a few minutes as well over the weekend if you guys have questions. But yeah, good luck studying. Let me know if you guys have any questions. And I'll see most of you for the makeup tomorrow as well. All right. Have a good one, everybody. I'll post these videos. I know we went through the end pretty quickly there. I'll post these videos on Canvas here at the end. Yeah, remember to upload your work to Canvas as well. All right. Have a good one, everybody.
See you.